So this is the walkthrough for the practice test on oxidation-reduction reactions. Where does oxygen take place? Where does oxidation take place? It takes place at the anode. So you can remember this however you want, but oxidation is where the electrons are coming from, and oxidation is when electrons are removed. So the oxidation takes place at the anode. The electrons are taken from the anode and go to the cathode. The cathode is where the reduction takes place. That's where the electrons are moving to. So that's really how it works that way and why it works that way. And that's the negative terminal is the anode, where the electrons are coming from. The positive terminal is the cathode, where the electrons are going to. So with that in mind, which of these would occur at the cathode? So the cathode is the reduction side of the cell. Okay, reduction means that the electrons are going to that side, to that electrode. So the one reaction out of these in which electrons are being added, which is what reduction is this one right here, choice A. In order to ensure that the electrons continue to flow in the intended direction, the anode should be immersed in a solution of salt containing the same ions as the metal that the anode is made of. The reason for that is you want to ensure that the electronegativity of everything in that solution as much as possible is equal to or less than the anode material. Because if you have a more electronegative ion in that solution, it's going to tend to disrupt the flow of electrons in the other direction. And the substance being reduced is the oxidizing agent. So it's kind of confusing, but we say that the oxidizing agent oxidizes the other species in the reaction. So the species that does the oxidizing is the one that's taking the electrons, and those species that's taking the electrons is the one that's being reduced. So it's kind of seems backwards, but the oxidizing agent is the one that gets reduced during the reaction. The purpose of the salt bridge is to prevent the buildup of charged particles. So as came up in an earlier question, you want the ions to be balanced, and you want them to be similar to the ions that are present in the anode or the cathode, whatever the case may be. But this salt bridge, as positive ions are being removed from the solution around the anode, from the solution around the cathode, and the ions are being added, positive ions are being added to the solution around the anode, then you can get this buildup of particles that are either positively or negatively charged on either side. And if that happens to too much of an extent, then again the flow of electrons starts to get disrupted because you're getting pushes and pulls of electrons in different directions from what you want. So the salt bridge allows ions to move in both directions to keep this equilibrium, to keep this balance of positive and negative particles on both sides of the cell. So balance the following reaction in an acidic solution. And we're going to get to this acidic part in just a minute. So the oxidation half reaction. Well, which species is being oxidized? Which is being reduced? So if we have oxygen, which has a charge, an oxidation number of -2, but we have 3 of them, that means we have a total of -6, which means we have a total oxidation for iron of +6, and since there's 2 irons, that means the oxidation number for the iron in there is +3. On the other side, we have iron as an element, which has an oxidation number of 0. So the oxidation number of iron has gone from +3 to 0, so it's gone down, which means the iron is actually the one that's being reduced. Obviously that means that the other part of the reaction is where the oxidation is happening, but just to confirm that, Again, if we look at oxygen with a number of -2, that means this carbon atom has a charge of +2. On the right-hand side of the reaction, we have 2 oxygens, which means -4. That means that this carbon has an oxidation number of +4. So this number has gone from +2 to +4. It has increased. It has lost electrons. Oxidation is the loss of electrons. So carbon is the species that's being being oxidized here. So the half reaction that we're looking at is CO becoming CO2. Now when that happens, the carbon is losing 2 electrons in the process. So we're going to add those 2 electrons over here. So this is the very basic part of the half reaction. The part where it says in an acidic solution, we just have to do a little bit more work because we need to also balance the oxygens that are present in the reaction. And when we're in an acidic solution, we balance the oxygens, because there's 1 oxygen on the left and 2 on the right, is that we go in and we add as many water molecules as there are oxygens that we need to balance. So in this case, we only need to balance 1 oxygen because there's only 1 difference between the right and the left. So I'm going to add 1 water molecule, and then I'm going to have to add to the other side now, because now we've got hydrogen on the left but no hydrogen on the right. I'm going to add to the right hand side 2 hydrogen ions. Okay, so this is how we balance the half reactions when it's in an acidic solution. I'll talk about the basic solution when we get to that. But so for an acidic solution, you add water molecules to whichever side needs more oxygens, and you add as many water molecules as you need to balance the oxygens. Then once you do that, you're going to go back over to the opposite side, and you're going to add as many hydrogens as you need, hydrogen ions, to balance the water molecules that you had to add on the other side. So we're going to see the same thing in the other half reaction. So in the reduction half, we have Fe2O3, and that's going to change to Fe. And in that process, the oxidation has gone from +3 to 0. So we're going to add 3 electrons here, because the difference between the iron on the left and the iron on the right is 3 electrons. We also are going to need to balance the irons. So we need 2 irons on this side. So then I'm going to rewrite this to make room for the other stuff we have to add to go with the acidic solution. We have 3 oxygens on the left. We have 0 oxygens on the right. So that means to the right hand side we're going to have to add 3 water molecules to balance the oxygens. And then we have to go back over to the left and add 6 hydrogen ions to balance the waters that we just added. So now we've got all the same number of every atom on both sides. We've taken care of the electrons. So now we have the oxidation half and the reduction half of those 2 half reactions. So when we combine the reactions, we got to do a couple of things. So we go back to the oxidation half, which was the CO plus H2O, and CO2 plus 2 electrons plus 2 hydrogens. And then the reduction half is the 6 hydrogens plus the iron oxide plus the 6 electrons. And on the right we have the 2 irons and 3 waters. Okay, so those are the 2 halves. Now before we combine them, the one thing that we have to do is we have to make sure we have the same number of electrons on both sides. Oxidation half and the reduction half must contain the same number of electrons. So you see here we've got 6 in this half and 2 in this half, which means we're going to have to triple the oxidation half. So we put a 3 there, a 3 there, 3 there. This goes from being 2 to being 6, and also this goes from 2 to 6. So now we're going to add the two halves together. And so we're going to end up with, on the left, 6 hydrogen plus Fe2O3 plus 6E plus 3CO plus 3H2O. And then on the other half, we have 3 CO2 plus 6 electrons plus 6 hydrogens plus 2 irons plus 3 water molecules. So there's the combined reaction. To get the final reaction, what we're going to do is go through and cancel out all the things that are the same on both sides. So that includes the 6 electrons. Those are on both sides. We're also going to be able to cancel out the water molecules, because there's 3 of those on both sides. And in fact, we're going to be able to cancel out the hydrogen ions, which means that all we're left with at the end is a balanced equation that looks like this. Fe2O3 plus 3CO yields 2Fe plus 3CO2. And you can see that we have 2 irons on both sides. We have 3 carbons on both sides. And we actually have 3 times 2, 6, and then on the right, oxygens, and we have 3 and 3 oxygens on the left, so that makes 6. So the whole thing is balanced. That's the final equation here. Okay, so now we have another oxidation reduction reaction. This one's taking place in a basic solution. With a basic solution, we have to do a little bit more work. We start out with the same process that we used in the acidic solution, but then we have to do a little bit of additional steps in order to balance the whole thing. So, to make it in the basic solution. So the first thing, again, is always, well, which reaction is the oxidation half, which reaction is the reduction half? So if we look here, we've got 4 oxygens, which means a total charge of oxidation of -8, which means that this manganese, you'd say it's +8, but you also have to take into account that this is a negatively charged polyatomic ion with a charge of -1. So that means the negative and positive are not quite balanced in this group of atoms. So the positive is 7 rather than 8, and that accounts for the negative charge. And then here, since we have CN, cyanide, as a unit on both sides, we're going to treat that the same. And we're going to call this cyanide with a state of -1. And then on this side, we've got 2 oxygens in this group, so that's a charge of -4. And since it's neutral, the manganese here has a charge of +4. And then the oxygen is -2, and since the overall charge is -1, that means that the cyanide group has an oxidation number of +1. So we can see that the manganese has gone from +7 to +4, so its oxidation number has gone down. That means it has been reduced. Whereas the cyanide has gone from -1 to +1, it has gone up by 2, so the cyanide is the species that's been oxidized. The CN yields this species over here. Now we're going to start by balancing it the way we did with the acidic solution, which means we've got 1 extra oxygen on the right, so we're going to add a water molecule on the left, and then we're going to add 2 hydrogens to the right to balance the hydrogens that we just added on the left with the water molecule. And then the difference between the acidic and the basic solution is that now we're going to go back, and for every hydrogen that we added, we're going to add a hydroxide, which means we have to add 2 hydroxides to this side. And in order to keep it balanced, we've also got to add 2 hydroxides to this side. All right, now The last part of setting up this half reaction is to notice or take into account that we've got 2 hydrogens and 2 hydroxides. Well, when you put hydrogen and hydroxide together, you get H2O, or water. So what we're going to end up with is 2 hydroxides plus the cyanide ion plus a water molecule, and on the right we're going to have the cyanide, the oxygen, and then we can form 2 water molecules from the 2 hydrogens and the 2 hydroxides. Okay, so that's the final product of the oxidation half. On the other side, when we've got the reduction half, we're going from MnO4 minus plus 3 electrons gives me the MnO2. Now I've got to do the balancing for the basic solution. So the 2 parts of that are, redraw this, because we have 4 oxygens on the left and only 2 on the right, we need to add 2 water molecules to the right hand side, and we need to add then 4 hydrogens on the left. Now that's the acidic solution. If it was in an acidic solution, we could stop there. But since we're in a basic solution, we now have to do the additional step of balancing the hydrogens by adding just as many hydroxides to both sides of the equation. So we're going to add 4OH here, and then we're going to add 4OH to the other side, and that means that we're going to end up with 4 water molecules on this side. Okay, so these hydrogens and hydroxides are going to get together, and they're going to form 4 water molecules. Alright, so now that we've got the 2 half reactions balanced, so now we're going to put the 2 halves together here. We're going to combine, and then we can cancel out things that appear on both sides, which will give us the final reaction. For the oxidation half, we had Cn plus H2O plus 2OH yields CNO minus plus 2H2O plus 2 electrons. In the reduction half, we have MnO4 with a charge of -1 plus 3 electrons plus 4 water molecules yields the manganese oxide plus 2 water molecules plus 4 hydroxides. Now, one of the things we're going to have to do is find a way to balance the electrons, because we've got 3 on the left-hand side of the reduction reaction and 2 on the right-hand side of the oxidation reaction. So since they both go into 6, we're going to triple the oxidation half, and we're going to double the reduction half. So that becomes a 3 for the water molecules. Get that in there. Plus 3 water molecules plus 6 hydroxides, and then 3 here. This becomes 6, and the number of electrons goes to 6. Down here in the reduction half, we're going to end up with 6 electrons. We're going to get 8 water molecules here. We're going to get 2. We're going to have 4 water molecules on this side, and we're going to have 8 hydroxides here. So we can start looking at how we can cancel out some of these things that appear on both sides of the equation. And the first thing that we're going to be able to cancel out is the water, rather the electrons. The 6 electrons appear on both sides. Water molecules appear on both sides of both equations. On the left-hand side, altogether, we have 11 water molecules. 3 in the oxidation half plus 8 in the reduction half. On the other side, we have 11. So we're going to end up with 1 water molecule left. We're going to have 3 cyanides 2 permanganate ions. What we're going to be left with is 1 water molecule on this side, because we had 11 on the left altogether and we had 10 on the right. So 10 of the 11 are going to cancel out, which leaves us with 1. And since we have 6 hydroxides on one side, 8 on the other, the ones on the left are going to cancel out. That's going to leave us with 2 MnO2 plus 3 CnO plus 2 OH. That's going to be our final reaction. Actually, the additional steps that we were doing were adding the hydroxides and combining them to make water and then canceling that out. So we have done all those steps in the previous slides. And the same goes for the final equation. The final equation is what we have here once you cancel out all the stuff that appears on both sides. That's the final equation. So we've got a galvanic cell with silver metal and magnesium. So we're going to figure out which is the oxidation half and which is the reduction half. The silver has the higher electropotential, so it is going to be our cathode. The electrons are going to go to the silver and away from the magnesium, which means that the oxidation half of this cell, which is going to be the anode, is going to be our magnesium. And that half reaction is this reaction here, but in the reverse. So we have magnesium solid from the magnesium anode, giving up 2 electrons to form the magnesium ion. And then at the other side, the reduction, which is the cathode, is where the silver is gaining 2 electrons to become silver metal, pure silver. So there are the oxidation and reduction halves and where they're going to take place. Oxidation takes place at the anode, that's the magnesium reaction. Reduction takes place at the cathode, that is the silver reaction. Indicate the directional flow of electrons. Well, if we have our magnesium and our silver, so this is going to be the magnesium half. Over here we're going to have the silver. In this solution we have silver ions. In this half we have magnesium ions. The electrons are going to flow in this direction from the magnesium to the silver along the wire that connects them. What is the voltage that would be observed? Well, the voltage is found by taking a look at the potentials of the 2 reactions. And we have the potentials up here, 0.8 and negative 2.38. The only thing you have to keep in mind is that the magnesium half reaction has been reversed. So we're going to have 0.8 and positive 2.38. So when we combine those two numbers, we get a potential of 3.18 volts. So that is the answer to the third part, 3.18 volts. And then include any necessary apparatus. So we've already got the solutions. So this is the 1 molar magnesium solution. This is the 1 molar silver solution, silver nitrate. We've got the magnesium metal, the silver metal. This is our anode, or negative terminal. And this is our cathode, positive terminal. We've got our wire here, that's where the electrons are going to go. And the one piece that's missing from this sketch is the way in which we maintain a balance of ions in the solution, and that is done by means of a salt bridge. So we're going to have this bridge connecting the two solutions, and inside that bridge we're going to have some sort of salt solution like a sodium nitrate, so that as magnesium builds up at the anode, magnesium ions build up at the anode, nitrate is going to flow into the solution to balance the charge. And in the other end, as silver ions leave the solution, these sodium ions are going to flow into that side to maintain the charges over there. So that is basically the entire apparatus. The last question is, what effect would increasing the concentration of magnesium ions in the magnesium nitrate solution have on the potential? Well, here's the way it looks. I'm going to simplify the drawing. I'm going to leave out the salt bridge, even though we need it for the circuit. So we've got magnesium ions on one side, and we've got silver bar, and we've got silver ions in the other side, and we've got the wire connecting the two, which is where the electrons are going to pass through. Okay, so the question, what would happen if we increase the concentration of magnesium ions on the left, so in this solution? Well, the principle here is essentially anytime you change the concentration, so we're changing the balance in this reaction. When you change the balance that's established in a reaction, the system, which is the reaction, is going to try to compensate to undo whatever it is you've done. So if I increase the number of magnesium ions in the solution, the way the system is going to compensate is by trying to remove some of those ions and return them to the magnesium metal. Well, the only way to return those ions to the magnesium metal is to pull back the electrons from the direction going toward the cathode. If I am pulling electrons in this direction, when I want them to be going in this direction, I am reducing the potential. Okay? So if I increase the ions at the anode, I am going to reduce the potential of the system, because the system is going to try to get rid of those ions by bringing electrons into that solution and getting those ions back into the solid. If I did the opposite, if I increased the number of silver, okay, then that would actually increase the potential, because those ions are already going to the bar to form the solid by drawing those electrons over. So if I add more ions, the system is going to compensate by pulling more electrons over here to get those ions out of the solution and bring back the balance that was there before you changed it. So adding ions to one side or the other is going to increase the flow of electrons toward whichever side you add those ions to. And depending on which side, you're either going to reduce, if you're going this way, you're reducing the potential, and if you add ions to this side, you're increasing the potential.